Hello, my name is Alex Elder, and I am going to be talking today about the Qualcomm IPA driver. I work for Lenaro, and I've been with Lenaro for about 8 years, and the last 3 years or so, I've been working on this project to get the driver for the Qualcomm IPA hardware accepted to the upstream Linux kernel. So today I'm going to be talking a little bit about that experience. So I'm going to start a little bit with a brief overview of what IPA is, and then a little bit of talk about what was required in order to get this project done. At different stages along the way, there were some different set of challenges that I faced, and so I'll talk a little bit about each of those sets of challenges at each time. And then hopefully I'll present a few things that I think I've learned along the way that hopefully are good insights or things that people that are valuable takeaway. So two other things I'll mention. One is that I do expect kind of a basic understanding of what it means to get code upstream in the Linux kernel. If you don't have that basic understanding, I think there's some other sessions to talk a little bit more about that this week. The second thing is that I have too many slides, and so I'm going to be moving through these somewhat briskly. I may not have time for questions at the end, but if I do, I will take them. Otherwise, I'm open to answer any questions people have sort of separate from the talk. So IPA stands for the Internet Protocol Accelerator, or IP Accelerator, and it's a component within Qualcomm system on a chip devices. It sits between the main processor, the AP, and a modem, and it basically carries data between the AP and the modem. And it's able to provide the AP access to cellular data networks. So the IPA is presented to the main processor as a network device, no different than like an Ethernet, and it's capable of doing some things so that the main processor doesn't have to. It does checksum offloads. It also does a thing called packet aggregation, in which packets received, for example, can be collected and then provided as a group to the AP so that it doesn't have to handle interrupts as frequently as it might otherwise have to. It's also capable of doing some more advanced processing of packets as they flow through the chip. They can do filtering, IP filtering. I say IPA filtering on my router, but I've got IPA on my slide, but I've got IPA on the mind. It's able to do filtering and routing and also NAT translation. These things are they're available by and supported by IPA, supported by the Qualcomm software for running IPA, but the support is not upstream yet. It's also, so the thing that these capabilities allow is that it allows the IPA can operate completely independent of the main processor, the main AP. What that means is you could have, for example, a Wi-Fi hotspot implemented where the SoC is able to provide data access to the internet to the Wi-Fi from the cellular data network, and the AP can go to sleep in that process. And in the process, you save a lot of power by not having the big high energy AP operational. This also is not supported upstream. I'd love to get it supported, but right now it's not. So the problem, Qualcomm, as I mentioned, has their own code that supports their hardware, including IPA. It's open source code. They call it downstream. It's used internally, but it's really public, and it's available on the Code Aurora Forum website. They use this software to support Android and other Linux-based environments. Windows, I think, is also supported. But they wanted to also support Chrome OS. And Chrome OS is not the same as Android or others, where Chrome OS requires their software to be actually upstream. And for hardware drivers, it needs to be in the upstream Linux kernel. And so Qualcomm had a problem. They had their downstream code, but it was not in the upstream kernel and needed to get it there. So the objective was to upstream the IPA driver. So early on, when they learned, or when they decided they wanted to do this, they got the input from Arne Bergman, who is the upstream ARM SoC maintainer. And he looked through their driver, and his assessment was that it was way too complex, much too complicated to be accepted in the state it was in. And so Qualcomm responded by initiating their own project to transform what they had into a much reduced functionality driver. So they did not support filtering and routing and NAT, and they only supported the, quote, embedded network connection to the AP that was the requirement for using it like on a Chromebook. And in the process, they started with, I don't know how big it was exactly, but it was over 100,000 lines of code. And I think they reduced it down to closer like 45,000. And so the result was IPA Lite, and it provided the basic operational features. They knew it would work on their internal, I mean, they were able to test it with the real hardware. And importantly for them, it was a subset of their downstream driver. And that was important because they were hoping that the upstream driver would just be sort of a close relative to the downstream, so that they wouldn't have to maintain two distinct source trees. So their hope was then that they could just adjust their downstream code as they needed in order to get it to be upstreamable. And then once it was upstream, they wanted to enhance the IPA Lite code back again to add back the functionality that was upstream. Qualcomm was very optimistic because they really had considerably reduced the functionality and size of the downstream IPA driver in IPA Lite. And again, they hoped it would be accepted without a lot of major changes, and their time frame was really, they were thinking it might be a matter of months to get it accepted. The reality was different. IPA Lite was not acceptable for upstream. I mean, it was considerably smaller. It did include some good design. It wasn't that it was bad. It simply was not in a state that would be able to be accepted upstream. Two things I tried to get across was that in order for something to get upstream, number one, you need someone to review the code. And if it was a gigantic driver or something that had sort of a funny look to it, in other words, didn't really follow some of the conventions, or did some conventions or did some practices and patterns that were different from what otherwise is normal in the upstream code, people won't review it. And if you don't get it reviewed, it won't get accepted. But so number one, you have to get someone to look at it. And the second thing is we need to get it to be accepted. And so that's another thing, but that's sort of another hurdle. So reducing functionality was very important. The IPA Lite code did remove a lot of high-level complexity, and it did reduce the code size. But the reality was that more would have to change. And there were sort of two classes of change, and I'm going to talk about each next. First of all, there's superficial changes. I mean, there were a lot of superficial problems in the code, and they're little silly things like the coding style. I mean, some of them are more than just silly, but for example, large functions, and which are just, upstream doesn't really like large functions. It's better to have a small function that encapsulates basic functionality some way that's easier to review and easier to understand. There were things like inconsistent indentation. I might have had my tab stop set wrong, but regardless, it needs to be sort of, it looked funny. There were very long symbol names. There were camel case symbols, other things like that. A bigger thing was really duplicated code. There's a lot of chunks of code where it's like the same function was duplicated twice, and it could have been refactored to be a single function with maybe options or parameters. So that needed to be done. There was dead code, and I'll characterize that in there's two types. One was that when they reduced the functionality of IPA to IPA Lite, they got rid of, for example, filtering, routing, those things. And there existed some other code that was related to that, but not used anymore, at least not for IPA Lite. So there was that kind of dead code. There's another kind of dead code which related to platforms that are no longer supported. So, for example, an older version of the hardware is no longer even supported in the downstream. But certainly, for our purposes, we were targeting a single platform. And so it supported platforms that were either no longer supported or were not going to be supported by the upstream driver. So that was also a kind of dead code. And then another one I'll mention is excessive use of IFDEF. I don't remember exactly what was there, but I know that there were IFDEFs, and IFDEFs are frowned upon. You really want to minimize those if you can. There were design problems too, not really superficial, but one of them, the first one here is really kind of a hardware design thing, and it really is not. I wasn't going to address it with the software, but basically the IPA hardware has a single queue feeding the AP, and a lot of the more modern high-performance network interfaces tend to have multiple queues, and they're able to do some improve their performance by using multiple queues and splitting traffic across them. But there are a few other things I'll mention. NAPI is the new, it's 15 years old. It's the API for handling interrupts for network devices. And basically, I think it was Arndt that said that no new network device driver, or rather all new network device drivers should use NAPI. And really, NAPI is just a generalization of interrupt handling, and it really just should be used everywhere. They use work queues for certain things. It seemed as though sometimes they weren't entirely sure whether things would have to be done in interrupt context or not, and so a work queue would be used. That was a design problem that needed to be reworked a little bit. Abuse of the device tree, I call it abuse, but basically what they did is they tend to use device tree in their downstream code as a place to put various configuration options. And I understand that doing that actually seems like a nice, convenient way of expressing some things like that. But upstream, that's not acceptable. Upstream, you really need to do just things that are hardware related, and even those things it needs to be reasonable, and you need to satisfy the upstream maintainer. And I knew that some of the things that were there were not going to be acceptable. They used an ioctl interface for some of their network control functions, and that was not going to be acceptable. And finally, they had a hardware abstraction layer. And this actually was, I think, a pretty good piece of technology that they have that simplified and generalized, normalized the interface they use for accessing certain pieces for different versions of the hardware. But I was told by many people that reviewers would be skeptical of using a HAL, a hardware abstraction layer. So basically that had to go. It may be that we'll have to add it back again in order to add functionality back at some future date, but we will have to see on that. So the plan was basically what Qualcomm had hoped, which is to start with the IPA Lite driver, modify it iteratively and evolve it toward upstream ready, and then post it for upstream review as soon as it was reasonable. And I agreed to that. Qualcomm agreed to that. I think everybody was in agreement, but the only difference was that upstream ready and reasonable were subject to interpretation. So challenges. So the first phase I will talk about is when I first started working on the driver. And one of the biggest, it was just a practical challenge. One of the biggest challenges was that the code was only available inside the Qualcomm firewall. And in order to access it, the only way I could do so was through a Windows laptop. And for a Linux kernel developer, working through a Windows laptop through a firewall is just kind of an unnatural way of doing work. It's not that it wasn't possible, it just made it more challenging. So the next challenge was that there was no real, at least initially, there was no hardware available to do tests on the code that was being developed and evolved and iterated. So again, it didn't make it impossible to do development, but it made it so that, I mean, for me, what it made me do is be extremely careful with every change that I made and, you know, review it very carefully, more so than I might have if I had had the hardware to do a test on, because then I could do a quick test, and if it worked, then it'd be fine, and I'd move on. And if it didn't work, I'd fix it and wait till it worked. So that was a challenge. The biggest challenge, and I think personally for me, the hardest challenge, was actually because of the schedule, the unrealistic schedule expectation. Qualcomm had their schedule and their order of months, but actually it could have been 6 months. Regardless, it was not realistic to get the work done that really needed to be done in order for the code to reach a point at which it's acceptable to be reviewed and accepted upstream. And I wasn't going to send code out that I knew was not ready for review because, you know, I could be ridiculed for it. And there's a certain reputation there with, if you are a developer, doing good work is something that benefits you in future work. So I didn't want to do that. So there was conflict there, and it was tough. It was a real challenge early on. I'll just mention that I think had I reset expectations a little bit better early on, it might have improved things. But the reality is, I think if I would have said it's going to be more than a year, it wouldn't have been acceptable, and that wouldn't have been received very well. The next stage of development was I posted in November of 2018 for review the first version of the code. And that was posted as an RFC. And at that time, I got a lot of good feedback. Actually, I think the main reviewer was Arne Bergman again. And I mean, I can't thank Arne enough for his involvement in this project. He, so some of the feedback I got is don't use global variables, don't use this register HAL if possible. I mentioned that before. Use BQL and look at the CODL and RFC 8289, which is just basically a generic way that the network stack manages the flow of packets to try to make sure that we don't drop packets or push things and have push too much data toward the network hardware that can queue it and therefore delay delivery of things. Avoid additional queuing, avoid excessive locking. One of the things that was there was a wrapper that sort of provided a nice simple interface around doing a DMA allocation. Well, they said, don't do that, just use the DMA allocation code. There was a comment about avoiding indirect function calls because of the Spectre problem and how we have to address that. And don't use ioctl and don't use bug. So these were, I say they're challenges. Basically, this was feedback. But what it meant was there's a whole bunch of work left to do. Even after all the work that I had done leading up to November 2018, there was still this kind of work to do. And as I said, I posted as an RFC because I kind of knew there was more work to do. Now, in May of 2019, 6 months later or so, I posted a real version of the code, which I thought was close enough to be ready for review upstream. And what happened then was unfortunate. Right about that same time, there was someone else from Intel who was also trying to post upstream support for a modem from Intel. And they found that there was not a common universal way of representing a modem in the kernel. And so he wanted to do a generic framework that might be able to do that in a generic way to handle all vendors and all modems. And that was not super well defined, and it literally took months afterward of me working with the one or two other people to try to define what it is. I offered to be the first implementer, the first one to actually use this new framework. And in the end, well, I'll tell you what happened at the end. But anyway, so we talked about it, and not much came of it. It became, in my view, it became sort of a difficult to even achieve. Second thing was that there was this, Qualcomm has a layering of two drivers that implement their network functionality. There's this RMNet layer over IPA, and there were questions about why that was necessary. So the next set of challenges occurred after they were accepted, after the code was finally accepted. I addressed all these things, but one of the things I did was when I posted this last series, I said I would like it accepted with no WAN, wireless WAN framework and no RMNet driver. So no changes to the way that the RMNet driver layers things on top of IPA. And actually, after just a very little bit of discussion, David Miller accepted it. And it was kind of surprising to me. But this code is very different from what I started with. It's very different from IPA Lite, and therefore very different from the IPA downstream code, the full driver. And so there are two code bases after all, which Qualcomm wanted to avoid. But I maintain one of them, and so maybe that's a little bit of a silver lining. I don't know. But another challenge now is that the downstream code is continuing to evolve independent of the upstream code. And so some of it is no longer familiar to me as I read it, so it's harder to read and translate into what needs to be done upstream if I'm going to do the same thing. And similarly, bug fixes in the downstream code aren't likely to be shared with me for the upstream code, and vice versa. So a few insights. The biggest thing I think is, well, one insight is that code quality is different between upstream and downstream, the requirements for code quality. Upstream quality is it. I mean, if it's not upstream quality, then it's not going to be accepted. It should be tested. It should work. It's expected to work, basically, but it has to be of high quality, regardless of how long it takes to get there. Meanwhile, downstream has to meet their schedule. They have to meet it. And the code doesn't have to be beautiful. It doesn't mean it's ugly, but it doesn't. The main thing is that it has to pass the tests and be done on time. Software lifetime. So the upstream kernel continuously moves forward. And with every release, we have new versions of the code surrounding each driver. Whereas for downstream, they will freeze a release for a platform. And at that point, they'll pretty much iterate on just that release. And then when they go to a new platform, they can start fresh with a brand new release. So that's a difference. Another thing is that for downstream, they can, when they start a new project on a new hardware, they can just say, all right, we're done supporting the old hardware. They've got the frozen release. Whereas upstream, basically every release has to support all the old stuff and the new stuff.
2 minutes.
Another thing is that the upstream kernel is a single unit, and any developer can touch any part of the kernel. What that means is that I can write a function and I can look at all callers of that function and make sure that they will never pass garbage to me as arguments. But downstream, they may partition different teams to work on different parts of the kernel. And as a result, it's going to be important for them to have each one is going to have a stable interface presented to the other so that their other teams can work without disruption. And then finally, upstream code generally assumes working hardware, and downstream code assumes working hardware, but it can also be used for hardware bring up. And for brand new hardware, it might be that things don't work the way they're supposed to. And so the downstream code will probably have to have some certain tests for things that are never likely to occur. Similarly, debug output might be very useful downstream to get things, get problems diagnosed early while bringing up hardware. But it's overkill for upstream. And the development process for downstream or for upstream is fairly well defined, but for downstream, Qualcomm has other code bases than Linux. And so they have to support different things. So right now, 2 platforms are supported. One is about to be supported, and a fourth is going to be supported very soon. I'm in the process of getting code to support new hardware upstream right now. We use the code to access a cellular modem on that ARM64-based laptop, and it works. There's still a little work to do on user space integration, but it basically works, and we'll be making that a little bit more available soon. In the coming year, I expect to be doing performance tuning and hopefully adding support for some of the more advanced features. And summary is the drivers upstream. It wasn't easy, but it got there. A quick note is that if you're going to want to get something upstream, it has to start out by at least looking like upstream code, which is a very vague statement, but basically little superficial things are going to prevent you from getting things accepted. So you got to get rid of the superficial things, and then once the superficial problems are gone, the design issues will be found. People do careful review of upstream code. So you should expect that reviewers will ask for changes. And then the biggest thing is that downstream and upstream have different requirements. And I think that it's no wonder that it takes work to adapt downstream code to upstream code, because they both have to function, but they don't have the same requirements. So I got some quick acknowledgements. I'm not going to mention them, but I got a lot of help along the way from all of these people, and I just really appreciate them. And at the last slide, I have a couple of references. Most of them are just posts to the upstream posts, but that's it. And that's what I have. I'm a little bit over, but I didn't go way over, and I finished my slides. So I don't think there's really any time for questions, but I guess what I'd like to do, I'll look on chat really quick. There's a delay, 5 minutes, okay. Anyway, so I think that's it. And I appreciate everyone for attending today. Thanks.